Hello and welcome everyone to our web seminar, Fast Track Digital Design of High Performance Pleated Filters. My name is Christopher Kühnle and I will show you how everything is done in GeoDict. Before we get to the details, here a brief overview of what will happen today. First step is we will import an existing CAD structure of a filter. Then we will generate a fitting cylindrical pleat and then add this cylindrical pleat to the existing housing, and after that prepare the flow simulation itself. Of course, we will then take a look at the results and see how the filter performs. If you see this, you might ask yourself why you should actually do this digitally. Whenever you're creating a new filter or a new filter design, there are two different ways. Approach number one is the analog way, where you pretty much produce a prototype, you prepare it for testing, you'll then run a lot of tests in the laboratory, repeat the entire process and see how your prototype pretty much delivered, or if it not delivered what you expected from that. This is then an optimization loop, which will take a lot of weeks till you find a product out of it. The same concept pretty much applies to the digital workflow, but with the difference that you can run a lot of simulations at the same time, all in one software which is data-driven, and adjust different parameters easily, which does not take weeks or months to actually produce it and get the material itself, but you can do it in the software digitally in only a few moments. Which means that you can shorten your development cycles from weeks or months to only a few days till you get your new product out of it. And all in one software. So the first step, as I said, is like the import of filter structures. In GeoDict, we can import OBJ or STL files, which are pretty much the basic formats for CAD structures. And whenever you are importing something into GeoDict, you can then specify the fluid and the material itself before importing it. And GeoDict will also give you a feedback on the mesh quality and if the structure is watertight. And if it's not watertight, then you might work on your CAD itself till it is watertight and you get feedback for that. The next step after that is, like I said before, the generation of a pleat, and in GeoDict we have a dedicated module for that which enables you to generate different pleats. So on the right hand side you see that we create different types of pleats easily in GeoDict. So you can create several layers of porous media itself, you can specify the pleat tip, you can specify the pleat height, you can specify the pleat count, you can also do things like M pleats, you can also of course adjust the inner and outer radius of your pleats itself, which means it's pretty easy and straightforward to generate different pleats and pleat designs in GeoDict, which helps you to create a variety of different pleats easily. So after that, after you've created all the different structures in GeoDict, you will then pretty much import the pleat inside of the structure and run the simulation. And after you've run the simulation, you can also then see things which are really, really hard to see in reality, but it's easily to see in the simulation, like how the flow directly behaves inside of the structure. This, for example, is a result of a flow simulation, and you can see here the velocity and how it behaves inside of the filter itself. And we will also dive into that directly into GeoDict later on when I will show you hands-on how things are done in GeoDict directly and how easy things are done in GeoDict. But as you can see here, you can get a lot of information out of your filter itself. And the good thing about digital software is that you can pretty much also automate it, because we are using a full Python API where you can pretty much automate your simulations, which means that you can enhance your productivity by using either cloud functions, which means you can run a lot of simulations simultaneously, or you can also run them, of course, sequentially, which saves time and value and resources if you are developing things in GeoDict directly. I will now move on to the software and show you how things are done in GeoDict, and we will go through all the steps, and then I will explain everything and how it is done in GeoDict directly. Okay, so the next step is pretty much opening GeoDict. this is our software GeoDict, and it's the first step, as I said before, is pretty much to import an existing CAD file in GeoDict. So the step for that is that we have a module which is dedicated for that, which says like import GeoCut, where you can import a cut structure in there. You pretty much browse in there and open the file itself. And then you are getting asked like, what is the unit in the file, which means like, i.e. the units in the file, millimeters, micrometers, nanometers, inches, and so and or different in here. In this case, for this file, it's meter, and we then suggest either the voxel count or the voxel length in GeoDict directly. So for this, in this case, it's pretty useful to use for showcasing. It's useful to use 300 micrometer as a voxel length, and then you can pretty much see the GeoDict then suggest how many voxels there are in X, Y, and Z direction. You can also see that we have all the material IDs over there. As a pore material, you can then choose whatever fluid you are using. It's pretty simple. You can just change it by using, for example, air or water or oil. And in this case, we will stick to oil, but it's, like I said, it's easy to change, and you can also change it definitely afterwards. And the next step is then like just importing the structure itself. For that, click on import, and GeoDict will then import the structure itself. This will take a few seconds, and after that, we will then take a look at the complete structure and see how it looks in 3D. All these things we are doing now are running on my laptop, which is not a large machine. It's just a commercial laptop, like I think 64 GB of RAM. This message pretty much shows you if you want to show the surface triangulation from the rendering, which is not needed in this case. So we click, in this case, no. So as you can see, it was pretty fast to import the structure itself, and then we can take a look at it in 3D and switch to the 3D view. And this is pretty much the structure we just imported, and you can, in this case, also definitely clip through the structure and see like how the inside of the structure behaves. It's like the structure itself, you can clip in any direction, X, Y, and Z, and pretty much slice through the structure. So, and because we want to get rid of the existing pleat, which is inside here, which is material ID number 5, it's like the purple material ID, as you can see, it's ID number 5. We want to get rid of that, and we want to put in a filter which is definitely the same size, because it should fit in there, but should have a different pleat count. So if you want to have the same sizes, you could either ask your CAD engineer to give you all the data which you need, for example, the outer radius, the inner radius, and the pleat valley, and so on and so forth. Or you could actually also measure like the dimensions in GeoDict directly. The easiest way to measure things in GeoDict is like we just concentrate on the material ID itself, which means that we can get rid of all the other materials just visually. We just uncheck everything else except for ID number 5, which is then our filter material in there. We should click on apply, and as you can see, we are just seeing ID number 5. We will turn off the clipping so we see the structure itself. Before the seminar itself, I prepared a small Excel sheet which enables you to pretty much calculate the dimensions of the filter itself. You pretty much type in the voxel length itself, which is in our case 300 micrometer, and then you put in the pleat start position, the end position, and automatically counts the length in voxels and the length in millimeter, and also for the outer and inner diameter. But we will do this now on the fly, but I would still suggest like using something like that which makes it easier for you to keep track of what your values were at the beginning. So how do you measure things in GeoDict? It's pretty straightforward. You switch over to the 2D view, and then you pretty much switch and slice through the structure itself. And as you can see, and the set axis at a specific point, the structure then appears, which means it's like the pleat starting position in Z direction. The first value is definitely then 32, which I imported directly in there. And as you can see, like if I go to 30, 31, no structure is visible, which means like the first slice is actually slice number 32. You do the same thing and slice to all the back till the structure is not visible anymore. And as you can see here, the last slice where it is visible is 315. I just typed in the values in here, 32, 315, which means like the total length of the pleat is 284 voxels, which means like in millimeter, it's 85.2 millimeters, which is pretty much 284 times 0.3. So we also need the outer and the inner dimensions of the pleat itself. And to actually measure this is like you go to structure and you start to clip, which means like if I clip on in the x-axis, as you can see, at some point, then I will just get rid of the structure itself. The easiest way is then to zoom in and just take a close look to this part over there. And as you can see, like at a specific point, I will then just crop out some voxels, which means like 12 is included, 11 is not included, does not change anything if I crop it out. So 12 is the first value, and you do pretty much the same thing at the opposite side. And in this case, it's 239. So we use 12 and 239 as the values in there. It automatically calculates the length inside, and we do the same thing with the inner dimensions. So inner dimensions is pretty much the same thing. We just crop in here till we pretty much reach the point where you do not see it anymore. So 53 is the last slice useful, which you can see. And in the other directions, it is 198 is in the last slice in there. You use these values, and then this sheet pretty much calculates everything inside. Also, I've taken a notice which says like our dimensions are of the structure itself is 252 times 252 times 363. I also made a small notice which the last slice is empty, which I will show you afterwards. So the first thing you want to do now is like get rid of the clipping and turn on all the structure again. So, and then you can see the full structure itself. And because we now have the dimensions of the pleat which we want to generate, we can soon go to the generation of it, but we first want to get rid of the existing pleat inside of GeoDict. To do this is pretty simple. We have like a process geo which enables you to reassign material. So for process geo, then go to reassign material IDs, and then you can reassign material, which means that we want to reassign our old material number 5 to the fluid itself, which is like inside of the filter. And this is in this case is ID number 00, which is oil. And if we click on OK and reassign, you will see that the old pleats will be disappearing, which means that they are not longer be part of the structure itself. So at this point, we want to save the structure as it is, because we will later then, like I said before, attach the new pleats to the existing housing and then have a new structure itself. So to save the structure, we go to File, Save Structure As, and then you pretty much save the structure as a GeoD file, and I say like without pleats. You save the structure itself, and then we can continue to the next part. The next part is actually to generate the pleat itself. For this, we have a module which is called BleedGeo, and we are interested not in the rectangular pleats, we are interested in the cylindrical pleats. For this, you click on the option of Edit, and as you can see here, we are pretty much interested in the inner diameter, we are using the outer diameter, or we could also do specific M-pleat patterns like this shape or different ratio, and you can also do even more different ratios in there. For showcasing, the most important thing you should always take care of is that the voxel length do match if you want to add a structure into another structure. So the first thing you should check is like the voxel length itself. So then go and add in, it's like change from micrometer, and then you see like it's 300 micrometer, and you can see these two values are matching, which means that later on you can attach structures to each other. Then a general procedure is that we pretty much, you can add different layers, multiple layers. It's pretty easy. You can just increase the number of layers in there and then type in the thickness of that. But for sake of showcasing, we just use one layer itself, which is then 600 micrometers thick. For pleat shape, I will just go back to millimeters because it's easier to see. And then we will definitely also take a look at our small calculation sheet, which we did before. So we learned that the inner diameter should be 43.8. So what you do now is then we put in the inner diameter 43.8 in here. And then also for the outer diameter, we learned that it's 68.4. Then we use the value of 68.4 in there. And you could then specify like the pleat value. And as you can see, then it will then adjust how the structure looks. You could increase the pleat count. You could decrease it. You could go for an M pattern. You could do a lot of things directly. And as you can see, it's pretty easy to generate something in GeoDict directly. So we will stick with those values, and we will use a pleat pack height at the beginning, which is very small, because it makes it faster to generate, and then we will just repeat the structure in that direction until we have the full length of the structure itself. So we now generate the structure, click on OK, and then click on Generate. And as you can see here, we have generated a pleat, pretty simple, it's pretty straightforward, which is now only very, very thin. To actually get it to the full length, it is currently 2 voxels length, and we will have to take a look at how many voxels they are in that direction, and it's 284, which means we have to repeat it with 282 voxels in that direction to get the structure come to the full length. To do this, it's just go for a process geo, then crop, embed, and add layers, and then just click on repeat. Then repeat in X direction with the value of 282. Click on OK, click on repeat, and now we have the full length of the structure itself. As you've seen before, we have now the material ID number 1, which is and we have the air in porous, but our material is oil. We will switch this later on before we actually run the full simulation. But as you might remember, our previous ID for the filter was ID number 5, and to not get confused and mixed up with the material IDs, we will also give this the material ID number 5, so things will not mix up. To do this, we will then reassign the material IDs, reassign material ID itself. Sorry, it's like material ID. We switch like the old material is ID number 1, which is the red thing, and we will then switch it to material ID number 5, new material ID number 5. We will then reassign it. As you can see, we had just reassigned the material IDs now, and we could theoretically from this point on go forward and add them to each other. To do this actually is you will then save your structure, and you save your structure then as, for example, pleats structure.gdt, save it in there, and then your structure is saved. So then we go back some steps where we just had the structure itself in there. Without the pleated, the pleats in there, and as you can see, we switch in here, there are no pleats in here. To really get the pleats directly in there, we use a module which says like a layer geo, and we want to add in a new material, a new structure, which we generate before, which are the pleats. For this, we will just browse in there and in the folder, and then we have the pleat structure.gdt. And as you can see here, those values for nx and ny are not matching. And if we just typed in an offset of 0 in there, then the material, then the pleats would be on the left side, which is not correct. I will just show it directly to you if we just import them without an offset. And as you can see, then we have the structure in there, the pleats in there, but we need an offset definitely. Then we will just undo that and go for an offset itself. We just choose the right material. We will choose an overlapping material if there might be some overlap. And the offset is then pretty much the difference, half of the difference between those two, which means the difference is 24, half of it is 12. And we definitely also need an offset in Z direction, because otherwise the pleats would start at the beginning. So we will take a look at our small cheat sheet, which says like the pleat start position in Z direction was 32, so the offset should be 31. And we will then run it. And as you can see now, if we then click in the structure itself, we have now the material in there. And for sanity check, then you can also go for 2D in there. I will undo the clipping, and you can then slice through the structure, and then you can see it matches perfectly to the old position in there. So there's no overlap, and it works out perfectly. So as you can see now, we have in here the materials in there. And the materials which are given in there are not perfect, so we should actually adjust them. But before you should do this, you should always take a look in Z direction to see if there's like an empty slice at the bottom or the top of the structure itself. In this case, there is an empty slice, and you should always get rid of the empty slice at the top and the bottom. The reason for that is pretty simple. The next steps will be to adjust pretty much and say like, this is the inlet, this is the outlet, and this is like an outer solid, which pretty much stops the solver from actually flowing through a solid material. But if there's an empty slice at the beginning, then there's a connection between the outside and the inside of the structure. And if we then assign the whole component, then it will be assigned to the wrong material. We should get rid of it, but I will definitely also show you what happens if you do not get rid of it. And how to get rid of it is pretty simple. I will show you that afterwards. So first things first, we will assign like input, inflow, and outflow. We go to the first actual slice, click on select voxels, you hold on shift and click on the areas which are the inflow. In this case, it's these voxels in there, and then we have two options, which says like, we have a lot of options, but those you should use are either flat fill component plane, which means it will flat fill one plane till it reaches a new material, and flat fill component is pretty much the same, but in 3 dimensions. So we will use flat fill component plane, and we want to assign it a new material which was not used before. In this case, I would suggest going for material ID 16, because the last material ID which we used in here is 15, and give it some information which helps you to do not lose track on what you wanted to do. So the easiest way is like something like inflow. Given it material information, and if you run that, then as you can see, these are assigned as an inflow. And only this specific slice is assigned as an inflow, which is enough. Then we will definitely assign something like then we will assign the outflow, but I will show you the issue with the empty slice at the top. So if we just click somewhere at the outside and click on flood fill component, because all the rest of material later should be solid. And if you assign some new material in there, which could be, for example, ID number 19 is like outer solid. And if you run this as a component, you will now see it will take a few seconds. And if you slice through the structure, as you can see, it will fill up the complete structure because there's a connection between the outer and the solid out of it. So we want to get rid of this and stop this from happening. The easiest way to actually do this is go for process geo and crop, and not repeat, but just crop it. You pretty much cut out the last slice, which is then cut out the last slice. It's one slice out of here. Click on OK, click on crop, and as you can see here, now the last slice is the slice you wanted to see. So we click on select boxes again, click in here, use then the flood fill component plane, use ID number 17 and call it like outflow, click on run, and then we assign the outflow, and then we go for this and that one. We want to flood fill the component. I will just choose material ID number 19 because like or I will use an ID number 14 because 16, 18, 19, they look very closely and it's easy to confuse. And call it something like outer solid. And then click on run. And as you can see now, if you slice down through the structure, there's no outer material inside of the structure and how it should be. So this is like how you assign the material itself, but we also, as you can see here, the material itself is not right. We just assigned one material which can be distinguished between different materials itself. So as you can see here, our fluid is oil, but our media itself is air in porous, which does not match because there should be oil in porous. So the next step is to actually adjust the materials itself. And for this, we then also go to process geo and go for reassign material itself and reassign material of material ID. So we want to change just the material of a specific ID. So the first one which should be changed is like ID number 5, which is not solid. It should be like oil in a porous media. Then we go to ID number 5, click on new material, and it's not a solid, it's porous, and the material which flows through the solid should be oil. And we give it some information so we do not lose track. Filter material. You click on OK. You click on OK in here and click reassign. And as you can see here, there's now oil and porous. And then we have like some things which also not right because the oil inflow and outflow is also correct. But the outer solid should not be oil. It should actually be a solid. So ID number 14 is definitely not assigned correctly. So what you do here now is we go for ID number 14 and change it now to a solid and give it an information which says like outer solid. You click on OK, click on OK, you click reassign, and now you have reassigned the structure itself. So we can then have a look at the structure itself. We can also then definitely slice through the structure and see this is like our structure itself. And from this point on, we can actually start to run the flow simulation itself. To run the flow simulation itself, we are having a module which says like FlowDict, because you want to run a flow. You want to simulate a flow experiment in there. We click on edit here, and it pretty much asks us about the materials because the constituent materials is the first step of it. And then you have a short look at it and see like all the fluid is always oil. It's like, because then we have like a green check mark. It says like it's oil, and all the other parts are solid except for ID number 5, which is oil in a porous material, which is definitely correct. to have like a real flow simulation, we need some parameters, which is like the permeability, because we need the permeability to predict the pressure out of the structure itself. You could either get this from microscale experiments or microscale simulations out of it, and for sake of showing, we just use 1e minus 12 in there, and we will go to the next step. And then we pretty much get asked, like, what type of flow are we having? Are we having a fast flow, or are we having a creeping flow? If you are unsure, please always use the fast flow, because then it will definitely, it's the Navier-Stokes-Brinkmann equation, and for fast flows it differs from the Stokes-Brinkmann equation, and the fast flow delivers always the right solution. If it is in a very creeping flow, then both results will match. But if it's a fast flow and you choose creeping flow, you will not get the right results. So I would advise you to keep the fast flow as a default. Then it pretty much asks you about the inlet material. And as you can see, if we just named it something like inflow, GeoDict directly assumes that is the inflow material. You could change it, but it's definitely okay. Then we have like different boundary conditions. You could apply something like a pressure or a flow rate. And in this case, we just, for example, you could switch the units in here. You could go for 16 liter per minute, for example. And then you have the outlet material ID, which is definitely also correct. And you assign them a boundary conditions, for example, the pressure as a boundary condition. And then we have a lot of domain boundary conditions, which means like how the structure behaves at the boundary. The periodic one is pretty much, the structure is periodically repeated at the boundary conditions. Symmetric, it means like it's like mirrored, and no slip means it is encased in there. For this case, it is encased in a closed wall, which is the right usage in this case. The solver tab can be normally just be leaving alone, and you can also check what equations we are solving in here and get more information about what we are actually solving in there. You could then just give it like your name, and it will then save it to a specific folder, which is your home directory, which you chose in the beginning. So then you pretty much give it a name, click on OK, and then you would go to run the flow simulation itself. I will not run the flow simulation now for the sake of showing, but I will definitely load in some results, and then we will take a look at how things are looking after the simulation itself. So I will just load some flow results in there. I will load the structure, and I load the pressure field inside of it. And then we can have a look at how things are behaving directly in GeoDict. It takes a few seconds till it actually has loaded a complete velocity field, because then we can choose between velocity, and we can also choose between pressure, and have a look at how things are behaving in different slices inside of GeoDict. So as you've seen, I've for showcasing, I just use a larger structure. This is why it takes a bit longer to actually load the flow field, but it should be done in a few seconds. And then we can have a look at the flow simulation itself. While it is loading, I will just also give a small advice for all the how you can automate things in GeoDict. Whenever you are running something in GeoDict, you can always, at the top, as you can see, we are able to create macros. And macros are pretty much recording what you are doing and giving you all the things which you are doing in a Python file which you can access, and then also switch the parameters. And then you can switch like from and say like I want to vary the pleat count, for example. Then it's pretty easy in the macro itself. Just record how you would do things normally. Take a look at the in the macro structure itself, and then switch some values in there, and then you can automate it directly in GeoDict and pretty much create a case study of different, for example, values, pretty easy, pretty straightforward, and have a lot of results then in a few hours, I guess. Yeah, this one is pretty easy to do. I will show you the macro dialog right after, then we've just loaded it in there. But just keep that in mind that you can always take a look what you've done already and also record everything without actually running the simulation itself. You can also just track the how things would behave if you actually would run the simulation. So as you can see here, we have now the structure, the volume fields in there, and we can uncheck the structure, and then you have the volume field itself. I will just go for a very short value in there, so we get rid of some very small artifacts. So it's 0.01 in here, and as you can see, this is like the velocity field throughout the structure, and then you can also definitely clip inside of it and take a look at it. You can also then go for 2D view and switch directions in there and pretty much see how everything is behaving inside of it. The good thing is also not only you can change like from actually the velocity, you could also switch to pressure in here, and you can see how this behaves. And what's also for me very interesting, I often choose like using some arrows, which helps to actually see how the flow is behaving directly in there. And I think it's pretty easy to see how things are behaving in there, and you can also then switch to 3D back and have a look at the structure itself and how the results are going. And then you can see pretty much what are the bottlenecks in the structure if you can look at it in 2D. And these are things which you cannot normally see in experiment, or only very hard to see in experiments. Yeah. And as you can see here, these are like the structure and how it behaves, the velocity fields in there. And from this point on, you could start to actually, run a small case study and see like how different amounts of pleats would actually behave and how they would change the result in there. Because as you can see here, I just load in the result again. As you can see here, for a volume flow rate of 16 liters per minute, the pressure was 54,302 pascals in the simulation. And then you could also pretty much easily switch the flow rate, but you just go for then flow experiment and then just change it from 16 to 40, for example, and see like how the pressure would change if you would run it with a faster flow in there or load in a different pleat itself. Yeah, and as I promised, we have the macro dialog, and as I said, it pretty much says like you can start macro recording, and if you do something like that, it then asks you how you should save it. And as you can see, we have like two buttons now, which is like record and run record. And record pretty much says like record what I want to do, but do not run the simulation itself. Just record what I want to do. And then you can, from this point on, you could record some things, like I could record this now, and then I could end macro recording and execute the macro itself. And then it will do what I've just suggested. And the good thing is also we have a session macro in here, and you can see these are all the things we've done in the current simulation. And you can pretty much click everything in here and create your own custom macro by clicking it together and save it, and it will then just create a Python file where you can edit all the things in there and create new structures. Before we get to the next question, I will just give you a small look out to what will happen in the future in GeoDict, and then we go over the questions. So in the future outlook will be the implementation of the techniques to simulate turbulent regimes. We are actually currently working on that. We are improving the usability of the entire workflow to make it even more easy for you to use it. And we want to give you even more individual Pleat configurations to give you even more testing capabilities. This is like the last slide, which says like, thank you for your attention. If you have any questions or want to test this by yourself, reach out to us, send us an email, and we will also deliver you some trial licenses of GeoDict to test it on your end and to see how things are running smoothly on your end. You can always also book an online session with any one of us, which is like Philip, Tabea, and me. And we are happy to share more information with you and also help you getting started in GeoDict. Bye.